The following is on the horizontal curve calculation, circular curve elements. This is a different example from the previous. So what we have is we've got a circular curve information is given as follows. We have a PI station of 6 plus 26.57. That is given here. So we know this point of intersection, and we have an incoming tangent bearing of north 56 degrees, 48 minutes, 20 seconds east. That means I'm coming up this blue line, and if this is the straight true north, that angle here is the 56 degrees, 48 minutes, and 20 seconds. So that's the bearing of this blue line coming in. Now, the tangent going out is a bearing of north 40 degrees, 10 minutes, and 20 seconds east. That means if I draw a straight line true north, that little angle here is my north 40 degrees, 10 minutes, 20 seconds east. So we've got a line coming in and a line coming out. The reason we'll need to do that is that's going to tell us what this intersection angle is. So we have to do this a little bit different than the last one. But we're still trying to find the PC and the PT. So we're going to look for this PC angle here and this PT angle here. Station. The PC station, the PT station. Now, when we do this, we still have to figure out our tangent lengths and the length of the curve itself. And then we'll figure out the long chord, the degree of curve, the external and middle ordinate distances. All right, so let's get started. So as before, we had all of the same curve elements. So we're going to use the following equations. The intersection angle is actually going to be the tangent angle in minus the tangent angle out. So again, if you're looking at this point right here, I know this is 56 degrees right here, and I know this angle right here is the 40 degrees. So that's how we're going to figure out our intersection angle. We'll use the equation for the length of curve from here to here is going to be 2 pi r times the intersection angle divided by 360. Tangent from the PC to the PI and the PI to the PT, that's our tangent length. And it's going to be the radius given times tangent of the intersection angle divided by 2. The PC station is going to be given as the PI minus the tangent length, and the long chord is going to be given as 2 pi, or 2 times the radius sine of the intersection angle divided by 2. Again, in this example, the intersection angle is in degrees. The PT station is this PC point plus the length of curve. The middle ordinate, the distance where you have the long chord and to the center of the curve, is going to be equal to the radius times 1 minus cosine the intersection angle divided by 2. And the external distance from this point here to the PI, center of the curve to the PI, is the radius times 1 divided by cosine of the intersection angle divided by 2 minus 1. Now in the example we were given this information. We were given the bearing information coming in and the bearing of the tangent line going out. We were also given the radius of 100 feet. So the intersection angle is the 56 degrees, 48 minutes, 20 seconds minus 40 degrees, 10 minutes, 20 seconds. So that intersection angle right here, this one right here, is 16 degrees and 38 minutes. So our length of curve is going to be the radius, the 1,000 times the intersection angle over pi over 180. And I'm doing pi over 180 because 2 over 360 is the same, or the 2 pi over 360 is the same as saying as 1, or pi over 180. Okay, so when I put this into the calculator, I get the solution of 290.31 feet. I do recommend you go through these examples to make sure that you get the same answers that I do when you're using your calculator. So the degree of curve is 100 times the intersection angle over L. So we figured out the intersection angle is the 16 degrees, 38 minutes, and the length of the curve is 290.31 feet. Plug it into the equation and we get the degree of curve as 5 degrees and 43 minutes and 46 seconds. Okay, remember the 100 is based on the station equation that our typical degree of curve is based on a 100-foot station increment in the English units. So our tangent is equal to the radius times the tangent of the intersection angle divided by 2. We plug it into the equation, so we say 1,000, which is our radius, times the tangent times the tangent of the intersection angle divided by 2. So we plug it in and we get a tangent length. That means the length from PC to PI and PI to PT is 146.18 feet. Now we're going to use the information over here that we got to solve for the station equations. Now we need these station equations because we're going to be laying out this curve, and we have to know where to start the curve and where to end the curve. So the PC station is equal to the PI minus the tangent, and the PT is equal to the PC station plus the length of curve. So the PI is 6 plus 26.57, and we subtract out the tangent length, and the tangent length was 146.18 feet, and we get a PC station of 4 plus 80.39. Now we're going to add the length of the curve, the 290.31 feet, to the PC station, and we're going to get 7 plus 70.70. Now, the next thing we're going to do is we're going to solve for the length of curve, the middle ordinate distance, the external ordinate distance. So what I have here is I just broke down the solution where I wrote down the equation and then plugged in my known information. So the long chord basically is 2 times the radius times sine of the intersection angle over 2. That's going to give me 289.29 feet. The middle ordinates, I've got the equation, the radius times 1 minus the cosine of the intersection angle over 2. So I've got 1,000 times 1 minus the intersection angle, the 16 degrees, 38 minutes divided by 2, and that gives me a 10.58 foot distance between where the long chord is to where the center of the curve is. And then the external distance is the radius times 1 over the cosine of the intersection angle divided by 2 minus 1. Now, when we plug in the equation, we know that the external distance is 10.63 feet. All right. Now, again, make sure you go through your calculator and confirm that you know how to plug it in and you know how to do the proper order of operation, because that's usually where we'll go wrong most often in these equations. All right. So that's it for this video.